And next speaker is Evelyne Miot from Paris, which will talk about some examples of dynamics of nearly parallel vortex filaments.
Yes, exactly. So thank you very much for the introduction and for the invitation to this conference. In this talk, I will present a joint work with Valeria Banica and Erwan Faou, which are both French people. So I'm going to start with a presentation of the model I'm going to consider. So we consider three-dimensional incompressible fluids So these fluids have velocity, v, which is a function belonging to, with values in R3. And they have a vorticity, omega, which is the curl of the velocity. So this belongs to R3 also. It's a function in space-time. So t is the time, and x belongs to R3. It's the position of x. Okay. And in this talk, we will focus on vortex filaments in such fluids So vortex filaments are very thin tubes in which the vorticity is sharply concentrated. So you can assimilate vortex filaments to very thin tubes. In which omega is concentrated. So there are tubes around the center line, around the curve, in R3, and this curve is parametrized by a function chi of t and s. So t is the time still, so I should say omega of t, and s is the parameter, okay, to parameterize your curve. So this tube has a thickness delta, which is very small, and they have a circulation gamma, which is a real number. So gamma corresponds, in fact, to the flux of vorticity around across the cross-section of the tube. Okay? So when the thickness of the tube tends to 0, you can assimilate your vortex filament to a curve, chi of t and sigma, like this. So this is my vortex filament, and gamma corresponds to the way in which the fluid rotates around the curve. And more specifically, in this talk, we will focus on the interaction of several vortex filaments. So consider n vortex filaments. And these vortex filaments are parameterized by functions chi j. Of t and s. They have circulations gamma j. Circulations. Okay, and in fact, we will consider a regime in which the n vortex filaments are all almost parallel to the same axis. So this is an asymptotic regime. which has been introduced by Klein, Maida, and Damodaran. In 1995. So we assume that they are all nearly parallel in the following sense. Nearly parallel filaments. So we assume that the functions Kj of t and s can be written or behave more or less as like this. So this is SE3, where E3 is a third vector of the basis of R3, plus a function plus a profile like this. So epsilon squared psi j of t over epsilon fourth, and s over epsilon plus little o of epsilon squared, okay, where psi j is orthogonal to E3, and where epsilon is a small parameter. So in fact, this should be Kj epsilon here. What does it correspond to? So instead of considering such a filament, you consider n filaments. So I have my axis here, E3. So this is the origin of R3. Okay. And so this is the height S over epsilon. So at the height S over epsilon, I have a vortex filament at position epsilon squared psi j of S over epsilon. Okay. So my filament will be like this. And I have several ones. Okay. And in fact, I consider very small tubes, very thin tubes around these lines. And the thickness of the tubes is supposed to be very small with respect to the distance between the filaments. So epsilon squared corresponds to the distance between the filaments, okay? And the amplitude of the perturbations with respect to the straight line here. And epsilon is the wavelength of the perturbation. It's not very well done on my picture. But the distance between the filaments is very small with respect to the wavelength of the perturbation in the s-axis. Okay. And in this regime, they derived to leading order in epsilon, when epsilon goes to 0, they derived the following system of equations. We get a system of equations for the profiles, psi j, which is the following. So I get a system of n equations, which will be my system star. So gamma j is the circulation of the filament. Alpha j is a positive parameter, which comes from the derivation, which is related to the vortex core. This is a parameter. Okay. So in fact, I put an I here because I identify R2 and C. Because in my derivation, I assume that the profiles psi j are orthogonal to E3, which is like assuming that they are vector field in R2. actually, or in C, okay? So here psi j can be a complex number or an R2 vector field. Okay. And psi j is a function from R times R to C, or R2. So the Laplacian is a Laplacian with respect to one variable, to a one-dimensional variable. So this is the system we are going to study. And in particular, we will study basic questions of existence, uniqueness for this system. So do they exist global in time solutions? In which functional setting we are going to look for solutions? And one question which is strongly related to the question of global existence of solutions is the one of collisions. Because when you look at the system, you see that the nonlinearity in the system of equations involves 1 over the distance between the filaments. So if two filaments get close one to another, then my nonlinearity blows up. Okay, so I have to study the possibility of collisions in finite time. Right. So I have first two remarks before studying these questions. The first one is that if we consider only one filament, so the first one, if n equals 1, then one gets a very easy equation, a very simple equation, which is the linear Schrödinger equation. So this is LS, I dt psi plus Laplacian of psi equals 0, or gamma, if you want, alpha gamma. Okay, anyway. So this is an equation, a dispersive equation, which comes actually from the linearization of another equation which is supposed to describe the evolution of one vortex filament. So this equation is known to be the linearized equation. Of the binormal curvature flow equation df, which can be written as dt chi equals d sigma chi cross times d sigma sigma chi of t and sigma, where sigma is an arc length parameter. And this equation has been derived in the last century by Darius in particular. So yes, it's the linearization of the binormal flow, assuming that chi is a small perturbation described by psi of the straight line. So assuming so around the straight line solution. Chi of t and sigma equals sigma E3. So in fact, if I take a straight filament and I linearize by means of psi, I get this equation. And as I said, the binormal flow equation is supposed to modelize the evolution of a single vortex filament. So it is a formal derivation. It's not proved rigorously, but still it's a good model. It appears to be, in some situations, a good model to describe the evolution of one single vortex filament. And my second remark is that if we assume that all the filaments are exactly parallel, so in fact, we consider straight lines that are all parallel one to another. So this amounts to saying that Kj of T and S can be written as Xj of T, not depending on S. Then we get rid of the Laplacian part in the system of equations, and we get a system of ODEs, which is called the point vortex system. And now everybody knows what it is, point vortex system. So this is the point vortex system which has been introduced today and also yesterday. So I xj dot equals or plus the sum for k different from j of gamma k xj minus xk divided by xj minus xk squared equals to 0. And this is a good model. It was proved. So it's called star star. And it is known that this system is a good description, it's a good approximation of the 2D Euler equations when the vorticity behaves as a sum of Dirac masses. So this was established rigorously. While for the vortex filaments, it's not known whether vortex filaments are stable structures. Okay, so everything is a model. So finally, the system is a combination of two effects. The first phenomenon is the self-induction of each filament, this one. And the second part corresponds to the interaction with the other filaments in a layered fashion. Okay? So before presenting the results concerning the vortex filaments, I will review some results concerning the straight lines, I mean the solution of the point vortex model. So this was already said today, but I prefer to write down the things. So this will be the second part concerning the point vortex model. Some non-results. So in fact, this is a Hamiltonian system with Hamiltonian given by H. Which is minus the sum for k different from j of gamma k, gamma j, log of xj minus xk. Let's put a square. Okay. And so it's a conserved quantity. And we also have conservation of the momentum of inertia, or the momentum. Let's call it I. So this is the sum of gamma k xk squared. So this is conserved. And we also have the center of inertia, C. which is the sum of gamma k xk. So this is conserved. And first, yes, and we also have, therefore, the conservation of another quantity which is called T. So this is the sum of gamma k, gamma j, x, j minus xk squared. Okay, so all these quantities are conserved. And it follows that if we have circulations gamma j having all the same sign, then we have global existence. Because otherwise, 2 point vortices would collide, and therefore the logarithm would go to minus infinity. And since the total energy is conserved, then we would need other point vortices to go to infinity, to escape. But it's impossible due to the fact that I is conserved. So we know that we have global existence without collisions for the point vortex system if gamma j positive for all j. No collisions if gamma j is positive or negative for all j. Okay, no collisions. Now, if n equals 2, so if I take 2 point vortices, as was already said, there are two situations. If, so we have a relative equilibrium. If the sum gamma 1 plus gamma 2 equals 0, then the pair of point vortices translates uniformly in time. So we have uniform translation. And if the sum is non-zero, we have uniform rotation. Around the center of vorticity, which is defined to be C divided by gamma 1 plus gamma 2. So we have rotation or translation. But anyway, the distance between the point vortices is constant. So in the case of n equals 2, there are no collisions. If n is larger than 3, we can construct, so in fact, it was constructed by, I think, RF, a beautiful example of collision in finite time in a specific situation in which gamma 1 and gamma 2 and gamma 3 don't all have the same sign, because otherwise we would have global existence. So this is an example of self-similar collision in finite time. And I write it down now because we will need it for the case of vortex filaments. So this is a self-similar collapse or collision. There exists a self-similar collapse. Not all of them are like this. So for which we can write xj of t minus the center of vorticity, c star, equals to xj of 0 minus c star. So in complex notations, I write it like this: 1 minus t over t star, exponential of a phase, which is a logarithm of 1 minus t over t star, something like this, for all j. Okay, so t star is the time of collapse, and lambda is a constant. So in fact, the modulus or the norm is continuous, but the phase rotates very fastly. So I get, and I have to choose the initial position, the initial configuration of point vortices in such a way that I get self-similar collapse. So I have no place anymore, but this will be a logarithmic spiral like this. Okay, so this is C star. And the shape of the triangle is the same for all time. So you just have a self-similarity of the triangle, of the configuration. And a last family of interesting solutions for the study of the vortex filaments is the one of polygons. For all n larger than, in fact, larger than 3 or 2 anyway, we have the existence of uniformly rotating regular polygons for which xj of t can be written as xj of 0 times exponential I omega t, where omega corresponds to the angular velocity, and it can be explicitly written in terms of the circulations. So it is equal to n minus 1 gamma plus 2 gamma 0 divided by 2r squared. So gamma, sorry, this is a small gamma. Gamma corresponds to the circulation of each of the point vortices. So we have to assume that all the circulations are the same. And r is the size of the polygon. So I get a polygon. So this is an hexagon. Okay. So I put gamma at each of the vertices of the polygon. And if I want, I can also put a central vortex here with circulation gamma 0, in which case I modify the corresponding angular velocity and I get 2 gamma 0. So in particular, it's possible to choose, and it will be important in the following, you can choose gamma 0 in such a way that omega is positive, negative, or 0. So you can really play with the central circulation of your point vortex to modify omega and to get some stability. So now I'm going to present a few results concerning the vortex filaments. So I forget about the straight filaments for a while. And I will present first the previous results on the vortex filaments. So Klein, Maida, and Damodaran studied, in fact, from a theoretical and numerical point of view, the case of the pair of filaments. So they studied essentially the case n equals 2. And they studied the linear stability when, and they proved that the system for the pair of filaments is stable if and only if gamma 1, gamma 2 have the same sign. If and only if gamma 1 times gamma 2 is positive. And they did some numerics predicting finite time collapse or collision, if you want, if gamma 1 and gamma 2 have opposite signs, and global existence if not. So no collisions if gamma 1, gamma 2 is positive. Okay? So they did a strong, and then presented strong numerical evidence of the fact that a pair of vortex filaments with negative and positive circulations lead to collision in finite time, which is not the case for the pair of exactly parallel vortex filaments, because we just saw that you never have collisions for pair. It's not me. Could be. And then, but okay, there were numerical predictions, okay, no rigorous results. And then the first, I think, as far as I know, the first rigorous results was obtained 10 years ago by Koenig, Pons, and Vega. So it was in 2003. So they proved in particular, in fact, they studied the linearization, no, not the linearization, but they considered vortex filaments to be small H1 perturbations of a collection of exactly parallel vortex filaments. So the ansatz is that we look for solutions such that psi j of t and s is equal to xj of t plus a function uj of t and s for all t and for all s, where uj is a continuous function with values in H1. Okay, so we have straight filaments. X1, X2, X3, for example, we take 3, and we consider small perturbations around these lines. That are given at each height S by uj. And in fact, the observation is that as long as the L infinity norm of uj is small enough, the filaments remain separated. I mean, if you consider a solution xj which doesn't have any collision, then you can control the distances between the straight filaments. And if you control moreover the L infinity norm of this guy, then you know that no collision between the vortex filaments can occur. And the second observation is that since we deal with one-dimensional functions, H1 is embedded in L infinity, and the space of continuous functions vanishing at infinity. So if we control the H1 norm of uj, we control the L infinity norm of uj. So the goal is to construct a global solution uj of the corresponding system of equations for which the H1 norm is not too large. And they obtained, in particular, local in time existence for all n and for all collection of straight filaments xj, as long as this solution is well defined. Okay? And for an initial perturbation sufficiently small in H1, and they obtained global existence so no collisions if n equals 2 or n equals 3 and xj of t is the rotating equilateral triangle. and uj of 0 is sufficiently small in H1. So this means that the collection of straight filaments has to be very specific because it's an equilateral triangle rotating with constant angular velocity. Okay, so this is the result they obtained. And the idea of the proof is to use an energy functional in particular. So for this global existence result, the main ingredient is to introduce this energy, which is the sum of gamma j squared times the gradient psi j squared, ds, on R, plus 1/2 of the sum for j different from k of gamma j gamma k times the integral of minus logarithm of psi j and psi k squared ds plus the integral of psi j minus psi k squared ds. So, in fact, if we look at this energy, it is conserved if psi j is a solution of the system for the vortex filaments, because, okay, when you get rid of the parts depending on S, you remove the first part with the gradient, and you retrieve the Hamiltonian for the point vortex system, and you also retrieve this angular momentum. So here, gamma j, gamma k place is also in front of this factor, and you retrieve the quantity t, which was conserved. So we retrieve the same kind of conserved quantities. And the point is that in the case of the vortex filaments, if we assume that psi j minus psi k behaves as xj minus xk at infinity, we have to renormalize this energy in order to obtain conserved quantity, to obtain well-defined quantities, because otherwise these quantities can't be integrable, because they don't go to 0 at infinity. Okay, I don't want to say no sense, but if psi j minus psi k tends to 1 at infinity, doesn't tend to 1 at infinity, this quantity is not integrable. So we have to divide, or the idea of Koenig, Pons, and Vega was to divide by the norm xj minus xk, here and here, and to say that by doing this, first you obtain formally well-defined quantities, which are still constant, because for the particularity of a triangle is that first all the distances are the same, because there are 3 points and 3 distances, and the second one is that the distances are constant in time. So by doing this, I don't change the fact that the quantity is conserved. Okay, and moreover, I get something, so they got something, which is coercive for the distances between the filaments, in the sense that the energy controls the L infinity norm of psi j minus psi k squared divided by xj minus xk squared minus 1 in L infinity of R squared. This is due to the fact that minus log x plus x minus 1 controls x minus 1 squared divided by 4, for example, if x is close to 1. So, finally, if the initial energy is small, then it remains small for all time. And therefore, for all time, the L infinity norm of this guy remains small, and therefore, there cannot be any collision in finite time, because otherwise this would become too large. Okay, so this is the idea. But this works only for the case of a triangle. So now, let's try to extend this result to the case of more than 3 vortex filaments. Yes, it works for n equals 2, actually, assuming that gamma 1, gamma 2 is positive. I mean, the product gamma 1, gamma 2 is positive. Because, yes, because otherwise, because we need a positive quantities in the energy. So this works for n equals 2, n equals 3, and an equilateral triangle. Otherwise, they only got local existence for the filaments. So now we want to consider the case of more than 3 vortex filaments. And we still consider the case of a rotating polygon, n-gon. So we consider xj of t to be a regular rotating n polygon. So I assume that gamma j equals 1 for all j. And let us start with the case of n equals 4. So I consider a square, a rotating square. And the theorem we obtained with Valeria was that if uj, the initial perturbation, is sufficiently small, so there exists a universal constant such that if this quantity is smaller than this constant, then this is sufficiently small. And if the initial perturbation is a parallelogram, so if psi j of 0 s, which is equal to uj of 0 s, okay, plus xj of 0 is a parallelogram, for all s. So I really have some symmetry assumptions. Then we have global existence and uniqueness. And for all time, the configuration remains a parallelogram for all s, and there are no collisions. First theorem, which is a kind of extension of the previous one to the case of 4 vortex filaments, sorry. But you have a very strong symmetry assumption. Okay. And in fact, if you don't consider an initial perturbation which is a parallelogram, you can obtain still a large time existence result, and it's possible to estimate the time of existence depending on the distance of the parallelogram configuration. So the closest you are to a parallelogram configuration, the longer you exist. Okay, first extension. And now we would like to consider more than 4-point vortices. Not point vortices, filaments, sorry. And we have to add more symmetry assumptions in order to obtain a global existence result. So the first natural symmetry assumption is to assume that we take our regular n polygon and we translate it by the same translation for all j. So this is a uniform translation, if you want. Translation. Like you just shift your polygon, assuming that psi j of t and s is given by xj of t plus the same u of t and sigma, t and s for all j. Okay. Then you get a linear Schrödinger equation for u, and therefore, since the H1 norm is preserved by the linear Schrödinger flow, if the initial perturbation is not too large in H1, then it remains not too large in H1 for all time, and therefore there are no collisions. Okay, but it's not very interesting because what you get for U is just a linear Schrödinger equation. So you can play with it, but after a while you're stuck. So you want to consider other kinds of perturbations. And the second kind of perturbation we would like to consider is a dilation, rotation of the polygon. So you take, instead of an additive perturbation, you consider a multiplicative perturbation. Psi j of t and s is equal to xj of t times phi of t and s, where phi is a complex function. So the modulus of phi corresponds to the amplitude of the dilation, to the size of the dilation, if you want, and the argument, the phase of phi, corresponds to the rotation of your polygon. And you assume this for all j. And then, so phi should be close to 1 in some sense, because it's the size of the multiplicative perturbation. And then, assuming this, you get a nonlinear Schrödinger equation for the perturbation phi. Yes, this is always my regular rotating n polygon. I really need this assumption. You will see in a while why. So then we get an equation for phi, which is I dt phi plus Laplacian of phi plus some omega phi over the modulus of phi squared times 1 minus phi squared equals to 0. So I recall that omega is the angular velocity of my polygon. I also assume that alpha j equals 1. Sorry, I forgot to mention it. Okay, I need this. And omega is the angular velocity. Okay, and in fact, this equation for phi comes from the fact that when I take the derivative, the time derivative of psi j, or the Laplacian of psi j, I realize that for all j, xj dot or I xj dot is given by omega, minus omega xj for all j. So it's the same multiplication, and it's also equal to the sum of xj minus xk over xj minus xk squared for k different from j. And this is valid for every j, which is really important. This is why we need to consider a polygon solution, a polygonal solution. Otherwise, we would have something here which would depend on j, and we wouldn't get the same equation for phi. I mean, we have to find an equation for phi which is consistent with the system of filaments. Okay, so I get an equation, and therefore I want to look and to study the global existence of solutions for this equation, which should govern the dynamics under the assumptions of dilation, rotation of the polygon. And this is the second theorem. But before stating the theorem, I would like just to emphasize the fact that this is an Hamiltonian equation, and the energy, the corresponding energy, is given by 1/2 of the integral of gradient phi squared plus omega over 2 times the integral of minus logarithm phi squared plus phi squared minus 1 ds. Okay, so this is constant formally. And in fact, you retrieve the same kind of energy as before. You remember there was this minus logarithmic part plus squared minus 1. So we get the same kind of coercivity property of the energy, assuming that omega is positive. And this is why I was saying before that you can play with the central circulation of the vortex in order to get omega positive. or negative. Okay. This is theorem 2. Stating that if the initial energy of my, the energy of my initial perturbation phi 0 is sufficiently small, then there exists a unique global solution such that phi minus the initial perturbation belongs to the space of continuous functions with values in H1, and such that the energy of phi is constant for all time. And moreover, I can assume that the modulus of phi squared minus 1 in L infinity is smaller than c times the energy. And I can assume that this is smaller than 1/2, for example, or 1/4, whatever you want, which is strictly smaller than 1. So what does it mean? It means that the modulus of phi will never vanish, and therefore the nonlinearity of the equation is well defined. So it's a regular one. And in fact, when the energy is very small, the modulus of phi will be very close to 1, and we get a Gross-Pitevsky-like equation. So in fact, the Gross-Pitevsky equation is the same equation when you remove the 1 over the modulus of phi squared. And this theorem holds true if omega is positive. Okay, I should have written this. So there exists an absolute constant eta 0, which is a number 1/2 or 1/4, or I don't. You can compute it explicitly. You can find it's a number such that if the energy is smaller than eta 0, then you get global existence. Just to make sure that if the energy is smaller than eta 0, then the modulus remains smaller than 1. And in fact, the modulus of phi does not vanish. Okay, so the solution we look for this equation are solutions for which the modulus is close to 1, because this corresponds to the perturbations we consider. So we have an equation, and we can now play a little bit with it in order to construct other kinds of solutions, and in particular, we can construct traveling waves solutions for this equation. You can also construct solutions blowing up in finite time for the L infinity norm, like phi behaves as like 1 over square root of t times exponential of I sigma s squared divided by t, something like this. So these solutions blow up in finite time. And you can also construct collisions in finite time, because this was our main question at the beginning. Yes, so phi of S and T is a function V of S minus Ct, and C is a velocity of the traveling wave, and in fact they exist if for all C, which is smaller than the speed of sound, which is in this context given by the square root of 2 omega. So you still assume that omega is strictly positive, and you can construct such traveling wave solution for positive velocity and smaller than the speed of sound. And there is a torsion in the direction at plus infinity and minus infinity changes, and it changes very little if C is close to square root of 2 omega. So you can estimate all these things. In fact, this was done for the Gross-Pitevsky equation and other Gross-Pitevsky-like equations in the case of the dimension 1, and also for 2D and 3D, but it's another. So you will see tomorrow, the day after tomorrow. Okay, collisions in finite time. So the first collisions we constructed thanks to this equation is what we call a Gaussian collapse. So in order to construct a collision, an example of collision in finite time for the vortex filaments, it suffices to construct a solution phi to that equation such that phi vanishes at some point and at some time. And in fact, we realize that if we set omega equals to 0, then we get a linear Schrödinger equation for phi. And therefore, it suffices to construct an explicit example of an explicit solution for this equation such that phi vanishes at some point. Okay? And this is the following example. So set g of s to be the Gaussian minus exponential minus s squared, and take the following solution. So we start with an initial perturbation, which is 1 minus the evolution of the Gaussian by the linear Schrödinger equation at time 1. So this is minus I Laplacian g. So this is phi 0, and therefore, by uniqueness, phi of t will be given by 1 minus exponential I times t minus 1 Laplacian. And therefore, at time t equals 1, I get 1 minus g of s. So if you set s equals to 0, you get 0. And the second example is the example of collision around the system of 3-point vortices. 2 minutes, okay. Okay, so I will go directly to the case of the pair of filaments. I'm sorry. This was pairs of filaments. And in fact, I will present you some, I'm going to present you some simulations for the pair of filaments around, so assuming that gamma 1 is equal to minus gamma 2 equals 1. And we did some numerical simulations in the following cases. Alpha 1, remember the vortex course, equals alpha 2 equals minus alpha 2 equals 1. And alpha 1 equals alpha 2 equals 1. So this case is not supposed to be a physical one because you remember in the derivation you needed alpha, the vortex core parameters, to be positive, but still from a mathematical point of view we think it's an interesting example. And the second situation is maybe the most interesting situation in which we are not able to construct rigorously existence of collisions in finite time. So let me present the simulations we obtained. So we still don't really understand why they behave like this. So in this example, we consider the first case, alpha 1 equals minus alpha 2 equals 1. And the symmetry, and we start with two filaments, psi 1 and psi 2, which are opposite. But then, as time evolves, the symmetry is no longer conserved, because in the case of alpha 1 equals to minus alpha 2, there is no symmetry for the corresponding system. Okay, so it's constructed around the pair of traveling vortex filaments. You remember when gamma 1 equals to minus gamma 2, the corresponding solution is a translating pair of filaments. So they will collapse at S equals to 0. But there is no symmetry, and then it will, okay, it's not very beautiful. So this is completely, this is not reality, it's numerics. Huh? Okay, the second example, for which we consider alpha 1 equals alpha 2 equals 1, and we keep the symmetry for all time. So here you see a beautiful collision in finite time, for which the symmetry was preserved. And in fact, we also constructed an example of collapse for which we have collision at 2 points, and we are not able to prove why this happens. So this is a mathematical challenge. Maybe not a challenge, but we are working on it. So we'll see this is the real part of psi, and you see that it vanishes at 2 points, which are symmetric with respect to the origin. Okay. So thank you very much for your attention, and have a good evening.